and study the full spectrum of options. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost, and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. But it's not just about a bigger form factor. Like, anybody could make a bigger form factor.
Any fool could make a bigger form factor. We not any fool.
Yeah, exactly. There are problems as you make cells larger. In fact, supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. And we did. We came up with this tabless architecture that maybe you've heard about, that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless. It's kind of a beautiful thing.
That's what these T-shirts mean, but it's very esoteric. It's like nobody could figure it out. But
yeah, we basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see, with simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like, basically the distance that electron has to travel, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs. This is, again, like, this is quite hard to do. So it's, nobody's done it before. And it really took a tremendous amount of effort within Tesla engineering to figure out how do we make a friggin' tabless cell, and having to connect that to the top cap. And it's there's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything. But
sometimes what's elegant and simple is still hard, and it took us a lot of trials, but we're happy where we ended up.
Yeah, I mean, everything's simple in recollection. After you simple, everything, it's hard until it's discovered, and then it's simple. So anyway, there's a lot of really cool things going on that enable tabless, and it's really due to a really great engineering. And then sometimes you get the tabs wrong, and you also lose a little bit of active area. It's really a huge pain in the ass to have tabs from a production standpoint.
Yes. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone.
Yeah, so when these, yeah, it's pretty great. And just to clarify that when we see these plus 16% or whatever the percentage range increases, these are the amounts due just to that particular innovation.
Yes.
So we'll list a whole bunch of innovations, and then when you add them up, you get a total improvement in energy density and cost. But these numbers are what refer to just this thing.
Yeah, and I want to stress, this is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So, yeah. It's a video of some of what's going on in the plant. Now, I mean, to be clear, it will take about a year to reach the 10 gigawatt hour capacity. So this is important to appreciate. Like when you build a factory, there's a certain capacity that you design to, and then it takes some period of time to actually achieve that capacity. So I would say it's probably about a year before we get to the 10 gigawatt hour annualized rate with the pilot plant. And this is just a pilot plant. The actual production plants will be more on the order of maybe 200 gigawatt hours, maybe more over time.
And thank you. But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. When thinking about the ideal cell factory, we have inspirations behind us in the paper and bottling industry, where from humble beginnings, over a century of innovation has enabled mass scale, continuous motion, unbelievably low manufacturing cost. And when we think about the lithium ion industry, which is really only in its third decade of high volume production, it has so far to go to achieve similar scale and simplicity. And that was the inspiration that we set out to the team as we thought about how to marry cell design and manufacturing in the best possible factory. And let's talk a little bit about what's in a cell factory. First, there's an electrode process where the active materials are coated into films onto foils. Then those coated foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cell is charged for the first time, and where the sort of the electrochemistry is set and the quality of the cell is verified. And we set out at every step of this process to try to take that inspiration we just showed and think about how we make those processes fundamentally better and more scalable. And one of the most important processes is where it all begins, the wet process of the electrode coating. And just to give you all a sense of scale, I'm going to walk through what's in that wet process. You've got mixing where the powders are mixed with either a water or a solvents for the cathode. That mix then goes into a large coat and dry oven where the slurry is coated onto the foil, huge ovens, tens of meters long, dried, and that solvent then has to be recovered. You can see the solvent recovery system. And then finally, the coated foil is compressed to the final density. And when you're looking at this, you're like, wow, that's a lot of equipment for one step, especially when you consider that little speck next to the coating oven is a person. This is serious iron involved in making batteries. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat. And that's what the dry process really is about. And in the most basic form, you can see it here on a bench top. Literally, powder into film. As simple as that.
I mean, it's hard, actually, just to be clear. So, if this was easy, everyone would do it. So it's not like dry coating electrode is actually easy. It's actually very hard to do what appears to be a simple thing. And it's worth noting, like, we did acquire Maxwell as like a little over a year ago, I guess. And it's certainly a good company and everything, but the dry coating they had was like like sort of I would call proof of concept. Since the acquisition, we've actually revved the machine that does dry coating 4 times. So we're in revision 4 post acquisition of the machine, and there's still a lot of work to do. So I would not say this is like completely in the bag. It's still a lot of work to do, and as you go from like benchtop to lab to pilot to volume production, there are actually major issues that you encounter at every level. It's not like, you make something work on your bench and bingo, now you can make a bazillion of it.
Absolutely.
It's insanely difficult to scale up.
Yeah, but if you do scale it up,
yeah,
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. But as Elon was saying, simple is hard.
Yeah. Yeah, I mean, to be clear, I would like not say that right now it's just totally working. It's close to working, but it's not, even now, at the pilot plant level, it is close to working. Well, it's fair to say it does work, but with not a high yield.
Yeah,
so
tens of thousands of cells, thousands of kilometers of electrode. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way.
Yeah.
I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
Yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there.
Yeah.
So, but this is a really profound improvement. Again, for people that know battery manufacturing, this is gigantic. We'll probably be on machine revision 6 or 7 by the time we do large-scale production. The rate at which the machines are being improved is extremely rapid. Like literally every 3 or 4 months is a new rev.
Yeah, and beyond the electrode, we continue to innovate on every other process step. So let's talk a little bit about assembly, which is next. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly, no stoplights and traffic lights or anything. You want the highway.
You want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
Yeah. So, yeah, you can sort of think about like the sort of the fundamental physics of a factory or something. Like, I think it's actually quite a lot like the rocket equation, where you've got basically in the rocket equation you've got your exhaust velocity and then the log of the start to end masses. So it's basically saying, how fast are things going and what percentage of the factory volume is doing useful work. And conveyance does not count as useful work. So
only the value-added steps.
Yeah. If you break the factory down into cubic meter sections and say, or smaller, it could be like 1 liter sections, and say, is a majority of this volume doing useful work? You would be astounded at how bad most factories are. They're like maybe 2 or 3%, including our factory in Fremont. So I think it is possible to get to at least 10 times that volumetric efficiency. So more like 30% ish, maybe more, and be 10x better, which means the factory can be 10 times smaller. And then the other thing is how fast are things going through the factory? It's like speed and density. The faster you go, like if a factory that's moving at say twice the speed of another factory is equivalent to 2 factories basically, and the company that will be successful is the company that with 1 factory can accomplish what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here is say, okay, how do we with 1 factory achieve what maybe 5 or even 10 factories would normally be required to achieve?
And the vertical integration with the machine design teams at Groman and Hybar and others allows us to really accomplish that because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be one machine and remove all of these unnecessary steps.
Yeah, I mean basically Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run. I think, just from a company standpoint and from basically achieving sustainability as fast as possible. But I think also for long-term competitiveness, eventually every car company will have long-range electric cars. Eventually every company will have autonomy. I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Manufacturing is hard, and hard problems are fun to solve. Okay, now let's talk about formation. In a typical cell factory, formation represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. Turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. The typical formation setup is you charge and discharge each cell individually. In our car, we charge thousands of cells at once. And we took our principle and our power electronics, leveraging Powerwall, vehicle battery management systems, and others, to dramatically improve the formation equipment cost effectiveness and density. 86% reduction in formation investment, 75% reduction in footprint.
So,
you want to take this one?
Sure. So essentially what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge. And I think there's probably room to improve even beyond that.
Definitely.
Definitely, yeah. So we're able to